I hope some examples were worked out during the tutorials regarding random definition of random variables and this notion of distribution function of a random variable. If you have any questions, I can take those questions now, or I can proceed with what I have planned to do today. Yeah, I should mention the following. Mm, uh, so, of course, I pointed out some examples of discrete random variables, uh, some examples where random variables take continuous values. Same way, you can have a distribution which takes only whose image takes only finitely many values. Um, it could take, it could be a continuous function, and it could be a mixture of the two also. Okay, so we are not going to study the most general type of thing. There are some kind of distributions which are known as singular distributions, um, about which we will not say much. So uh, we will mostly study a distribution function associated to a random variable which is either discrete or continuous. But there can be, first of all, mixture of two, and there can be many more complicated type of distributions. Yeah, even in continuous distributions, there can be what are called singular distributions. So these are quite complicated. By the way, I mentioned some properties of distributions last time, and in fact, those properties uh, characterize all functions which arise as distribution function. If you recall, uh, so f is a function from here, real numbers to 0, 1. It takes values. Um, yeah, f of x is uh, bigger than or equal to f of y if x is bigger than or equal to y. And so, um, yeah, f is continuous from the right. So limit uh, h goes down to 0, f of x plus h. I may have written it in a slightly different manner. This, and was there any other property? I don't know. I don't think so. Let me just check very quickly if there was some other property which I. Hmm.
So there was one more, right? As x tends
Yeah.
to minus infinity. Yeah.
Ah,
That
yes, yes, of course, yes. Yeah, yeah. Uh, this is, of course, important. Limit x goes to minus infinity. These are obvious things, but one should not omit them. This is equal to 0, and limit x goes to plus infinity, f of x is equal to 1. Okay? Yeah, of course. Uh, yeah, I mean, without this, also these two conditions can hold, because as x goes to this, it could turn out that this is half, and maybe this is 3/4. So all these three are to be stated, in fact. Then you can ask, so the question is, so yeah, this is what I want to say. Suppose that f satisfies the above three properties. then uh, yeah, there exists a random variable. Well, you can say there exists a probability space omega f p and a random variable x from omega to p. No, sorry, what am I writing? Real numbers. Such that f is equal to fx, the distribution function of x. Okay, so we will leave this at that because I don't want to go further and tell you how to construct these x and so on. You will realize it's a very natural thing to do. Okay. Uh, Now what we want to say is the following. Uh, yeah. So see, f determines. I mean, once you have the distribution function of a random variable. Okay, but before I proceed further, let me say this following thing. Whatever I was saying at the beginning, you see, it could be that I can just have something. Uh, so hmm, so this is my copy of real numbers, and then this is of course 0, a line corresponding to y equals 0 and y equals 1. Sorry, it doesn't look like a parallel line, but okay. So I can have something, some distribution function. So maybe this is minus 1, and maybe this is 0, and then 2, and so on. So I could have something which looks like this. So whose graph? So I'm going to draw the graph of f, graph of f can look like something like this. 0 up to 0 up to minus 1, but when it is minus 1 it could be maybe half, and then up to 0 it remains at half, and at 0 it becomes a little more, and this is a line, by the way, x equals 1, so y equals 1. Let me not say that. And then it could become like this. Sorry, I should, yeah. So like this for some time, maybe up to 2. 2 is here. And then it is flat again. Okay. So let me draw this picture properly. So this is my graph of fx. So y equals fx. And so you see, so just let me draw this properly. So now this will correspond to some distribution, right? I just, yeah, this will correspond to some distribution. You can see that it takes discrete values sometimes and then it becomes continuous like this. Okay. So you can draw almost anything, from any graph, uh, subject to these properties, and then it will turn out that this corresponds to some probability space and some distribution function of a random variable. Okay. All right. So let me move on. Okay. So today I want to talk about this theorem. It's in fact the next section, what is called the law of large numbers. Hmm. So you see, mm, um, in order to motivate this, so but first maybe I should state the theorem. So let omega f p be a probability space. Uh, A1, A2, AN. Um, uh, pairwise independent events such that probability of AK is equal to small p for all k, make it equal to 1. Okay. And let uh, yeah, let's just write Sn. Okay, Sn is equal to summation k equals 1 to n uh, indicator function of AK. Okay. And let's look at this. So Sn by n, this is a random variable. Okay. The random variable.
Sir, maybe I don't know this. So what does I subscript AK mean?
Huh?
So
Oh,
what?
this is, I recall, I think I have used this notation before. Recall, I said that just now, IA is the indicator function of A. Indicator
Understood.
function
Okay.
of A. So IA is equal to, I'm glad you asked. So X is, oh, sorry, 1 if X is in A. Okay. 1 if X is in A. And 0 if X is not in A. Okay. So Sn keeps count of how many times this, okay, these events have occurred. Okay, n goes from 1 to n. The random variable that counts. So let me, that counts, blue color, counts the average. So number of occurrences of the events AM to AN. Okay. So uh,
Yes, sir.
so the thing is that it's very. I want to say that you can have a situation where this type of thing happens, but in this context, omega, is a bit difficult to describe. Hmm? So if you fix n, I can explain to you what omega is for that. So it's like, you think of AK, so you think of an experiment, a random experiment, uh, and you have your favorable event A. Okay. Now you conduct that experiment many, many times. So A1 is the event that A has occurred the first time. A2 is the event that A2 occurs the second time. A occurs in your second time. Okay. And blah blah blah. AK is the event that A occurs, the favorable event A occurs in your kth trial. So, for example, you may think of a coin toss experiment. You just keep on tossing coin, and AN is the event that head has appeared in the nth trial. Okay. So, at other trial, I mean, other than the nth one, we don't care what is the outcome. Just at the nth trial, you want your favorite event A to occur, and that is my event A. And if you believe that successive repetition of the same experiment, like coin toss, they are all independent events having same outcome, I mean probability of A occurring, then A1, A2, blah blah blah, AN, they are all independent events, and their probabilities are the same as of occurrence is the same as probability of A, which is P. Okay, so this is a way to think of it. So if you just say, okay, I repeat it n times, then it's easy to write out what is this AK. But we don't even want to restrict our n, and therefore it is written like this: A1, A2, etc., AN. And we want to think of n as a variable also. Okay. And in fact, so yeah, so this theorem that we are going to say it has a lot of implications. Uh, you see, classically, you may, so you have a coin and you don't know if it is biased or unbiased, and you may think that I just keep on tossing the coin and then write out a frequency table how many times, so I toss it 100 times, and then I just write down the frequency table how many times head has occurred, how many times tail has occurred, and you keep on doing this many times, and then see the average number of times head has occurred. Okay, and note that down each time, and you think that if the average number tends to a certain particular number p, and that number has to be the probability that in a particular toss head has occurred. Okay, so this is a reasonable, so in fact um, so this is what prompts us to even say, uh, a coin toss experiment results in head with probability P. Okay. But theoretically, you have already described what is the probability P, probability of head occurring, and you said that equal to P, and probability of tail occurring, therefore, is 1 minus P. Have two urns and you draw a ball from one thing and then put it in the other, and then, so when you do these type of problems, they are to be thought of as models. Okay, and you have, for example, n cells and or n mailboxes, and you have some bunch of letters, you distribute those letters into the mailboxes and so on. So that's a model. So every problem we do is a model which is perhaps applicable in a wide variety of situations. Okay, having said all these things, let me now state the theorem. So, so did I say that P is the? Oh, okay, I already said that. Okay, here. Okay, this is already stated. Uh, Let me just state this theorem formally. And this is called law of averages or weak law of large numbers, one of these two. Okay. Theorem. So, given epsilon positive, we have. So I'm not going to repeat the hypothesis. Everything is notation. Everything is written down. You look at the probability of the event that minus epsilon less than average. So Sn by n. This is some random variable. Okay, if you like, I can write like this. I think this is, in fact, maybe more simpler to understand. P minus epsilon less than P plus epsilon. Okay, this goes to 1 as n goes to infinity. Okay, so what is P here? P is, so let me say this, where at least once again, where P of AK is equal to N, P for all K bigger or equal to 1. Okay. So recall that we assumed A1, A2, AN, etc. to be pairwise independent. That is part of the hypothesis. I'm not going to repeat that. So proof. So several steps, but first step is convert it into a coin toss problem. Just for convenience. Coin toss problem. So AK is the event. Is the event that the outcome of the kth toss. Kth toss equals is kth toss is head. H. So assume that the coin is biased. Assume that I should have said this first, but I already said it without writing. Assume that probability of H is equal to P, and therefore probability of tail is equal to 1 minus P, which is equal to Q. Okay. Yeah, so I have said that. Now let what is it that I want to say? Let Hn equal to number of heads in n tosses. Okay. So this you can think of as Sn actually. So so this this may be thought of as yeah, corresponding to Sn. In other words, so probability of Sn equals K is the same as probability of Hn equals k. Okay. Number of times, so each time head occurs. So you see, so it's, I wrote here, AK is the event that this outcome of the k to the power is h. Let me change that to AK prime. So since AK corresponds to, because I want to set up correspondence. So let me write that. Since AK corresponds to, mathematically it's all the same, corresponds to AK prime. Right. Yeah. So there is mathematically there is no difference between these two. Yeah. So as random variables, Sn, so you can say as random variables, is that correct? Or maybe as distribution functions. Let me not make this say anymore because, so, okay. So now what we are going to do is after this, you just deal with the Sn. So we may as well write this. Okay, so probability of Sn. So, okay, let me say this before I write this. You see, you rewrite this in the following form. So, where is that? Where is the statement? So, I compute the probability that Sn by n is bigger than or equal to epsilon, p plus epsilon. And I also compute the probability that Sn by n is less than or equal to p minus epsilon, and I show that as n goes to infinity, each one of these go to 0, and that would already imply that I mean, as n goes to infinity, this quantity here goes to 1, so that will prove the theorem. So I just write this before I do the calculations. We shall show that, we will show that probability of Sn bigger than or equal to p plus epsilon. Okay. Sorry. This is okay. Pn by n. Sn by n. This goes to 0. Here I put plus or minus as n goes to infinity. Okay. Sorry. This again will cause problem. I should not write plus or minus. You have to be careful. So similarly, okay. We'll also show probability of Sn by n is less than or equal as n goes to this thing. P minus epsilon also goes to 0 as n goes to 0. And this would imply this will prove the theorem. Okay. So therefore let's compute that probability of Sn by n bigger than or equal to p plus epsilon is equal to probability of Hn is bigger than or equal to n times p plus epsilon. Okay, and this is equal to probability. So let us give this some name. Let m is equal to integer part of. Okay, so I write like this. Actually, greatest integer less than or equal to least integer bigger than or equal to NP plus epsilon. So what is called ceiling function. Okay, so if it is 5.1, you have to take m to be 6. Okay, that is the meaning of this symbol. You will see the moment I write it. This is equal to k going from m to infinity, m to n. So in n tosses, I'm counting, right? So n choose k, p power k, q power n minus k. So this is something you all know, right? When you toss a coin n times, what is so? Okay, I skipped one step. The step that I skipped is k equals m to n, probability of hn is equal to k. So you can almost forget about this n. We have fixed n for a minute. And now look at number of times the heads appears in n tosses is equal to k. So if you toss a coin n times, number of times heads appears is equal to k is your event. And what is the probability of that occurring? It is k successes, so p power k, q power n minus k. But after you specify which k event gave you that, but without specifying, so there are n trials. You can choose the k success trials in n choose k ways. That is why you have n choose k times this. Anyway, this is a very simple and elementary thing. Okay.
Sir,
Yes.
I have a doubt. Like, so this theorem is a verification of,
K
like,
theorem
so
is
what?
valid for.
No, no, no. What exactly is this theorem saying? As in, like, is it just verifying that the probability is right? Like, whatever probability we started with, that's the correct probability. Is that?
This that is that's exactly a philosophical discussion, because for us we have already described what is a probability. I mean, the moment you say what is your probability space, probability of head is defined, probability of tail is defined. I mean, given to you, it is what we call, see, it's already assigned to you. What this is telling you, see, the philosophical implication of this theorem is the following. Okay, intuitively, what is our understanding of probability? Okay,
Yes.
intuitively our understanding is that we say, so the chance or you know the probability, likelihood, which you measure in terms of numbers between 0 and 1, likelihood of head occurring in large number of trials, okay,
Okay.
is going to be a certain number. That number, let us call that P. Okay.
Hmm.
And therefore, now you abstract it. So suppose I toss a coin only once. What is the probability that head will appear? That's equal to P. Okay.
Yeah. Hmm.
So here we are proving a certain theorem. What does it say? The average number of times head appears in n trials is uh, you know, well, that need not go to P. All we are saying is the probability of this random variable. So you see, so this is, I should emphasize this. This is a random variable and not a number. If it is a number, you cannot talk about probability of some number being between two numbers. So this has to be, there's a lot to say about this. First, so do you understand that this is a random variable and not a number? I already sort of indicated it by writing this expression. This is a random variable. So I have even written that down here. It's an important thing. It's a random variable. So what is it that we are computing? We are computing the probable. So this is same thing as, okay. Uh, Okay, so this is a certain event. What is that event? Probability of a certain event E. Let me write here En. En is the event that omega in your capital omega such that I can compute Sn omega. Sn omega divided by n. Okay, this is now a real number because you have stuck a omega here. This is equal to, this is caught between these two numbers, p plus epsilon and p minus epsilon. So, okay, I put here equality, it doesn't really matter. I just remove the equality here. Okay, so this is what you are computing. And if you expand on this, what this means is omega belongs to one of these AKs. Yeah. So this is average number of times. So you can rewrite it. Let me squeeze it in here. Equal to omega in capital omega, such that average. I can write it in words. Average number of times omega belongs to AK is in the interval p minus epsilon to p plus epsilon. This is a expanded version of this set En. Okay, sorry, I had to really squeeze that in. So this theorem is sort of comforting that um, whatever intuitive feeling that you have, which prompts you to say probability of head must be uh, P and probability of tail must be Q. Or if you have a fair coin, probability of head is half, probability of tail is half. You are prompted to say it by conducting certain experiment a large number of time. Okay. So actually I should repeat this. I should clarify a little bit more. It is not enough if you just toss a coin some 1,000 times and then you find how many times head has appeared, how many times tail has appeared. You must do this several, I mean, 1,000 times, and then again another 1,000 times, again something, and so on and so forth. It doesn't say, you cannot fix a number and talk about it. If you fix a number and compute it, it may be outside the range. See, given your epsilon is already given, okay, and when you, because you see, it can so happen that in a particular toss, 1,000 tosses, it could so happen that you got only 100 heads and then 900 tails. Okay, this may lead to suspicion that the coin is not fair. But whatever you think you have experimented with, just only once. So you do it another maybe 1,000 times or maybe 2,000 times, and then you keep on recording the frequency. Or in other words, you just record the don't limit your numbers, keep on repeatedly applying this n times and allow n to go to infinity, whatever that may mean, and then you keep looking at these averages, and that averages, okay, tends to some number with probability equal to so this is yeah, I mean, it's a complicated thing. It conveys a certain message which is rather very subtle. I mean, there are other notions of convergence, and this is what is called convergence in probability. Okay, let me just briefly say that because I said this. You see, when you have a random variable, you have a function associated to it, that is distribution. Okay, distribution function. Now you can form these random variables Sn by n, and corresponding to each one of them you have the distribution function, And we are not saying that these distribution functions converge to some limit, namely 1 or something, constant function. We are not saying that. What is being said is something. So, sorry, distribution function tends to the distribution function of just if just single coin toss experiment with probability of head equal to p. We are not saying that it tends to that. We are saying that in probability, so there are in probability. So when you say in probability, again, it's only a matter of, you cannot say event en occurs um, with I hope I have already conveyed. I think if I expand it even more, perhaps it's confused. But you think about it. This is nothing more or nothing less is true. Just this statement is what we are making. Okay. You try
Yes.
to make a more ambitious statement, it may turn out to be false. Even
Yes.
when you know that the probability of head is p and probability of tail is 1 minus p. We move on. So, okay. So now I already spent so much time, but it's well worth the time, I think. So now what we are going to do is use some manipulation, some tricks. By the way, it seems that this theorem was proved by J. Bernoulli. There's a whole family of mathematicians, Bernoulli, around the year 1692. So here you write K. So yeah, so let me write this. K is bigger than or equal to this, and then uh, so let me say this. The next step itself, some I want to look at my notes and then say how to proceed further. So probability, this is already wrote that. Okay, K is bigger than. Yeah. So before I write this next one, I want to say something. So each term in here is going to be modified by something slightly different. Okay, and then we will write an inequality. Okay, something more here. So let lambda be positive, and then look at this. Then e power k lambda, so is bigger than or equal to e power k times np n times p plus lambda, p plus epsilon, because well this k lambda, I think, this is lambda times, if k is bigger than or equal to this m. Okay. All right. So we are going to replace this one. Unfortunately, I have to do this. Therefore, I want this side to be bigger. So I will write here probability of Sn by n bigger than or equal to p plus epsilon is less than or equal to summation m choose k here I first write this weightage e power instead of, yeah, I'm going to take this to this side, lambda k minus lambda times np plus epsilon. Okay. Yeah. Okay, and of course p power k q power n minus k. Okay, and also here after doing this, I'm going to write here k equals 0 to n. This is what I want to write. Okay, so write that, and then let's proceed. So this needs to be there's a less than or equal to, let me write here, e power minus lambda n epsilon, that will stay outside, and remaining things you will have e power k lambda minus lambda np. There's some n I'm missing here. Already I'm having trouble. Just let me just look at my notes. No, that's okay. That's okay. Yeah, that's correct. So, okay, fine. So this e power, this is a crucial thing. I write here k. It's a tricky proof. You got stuck at the first step. So before proceeding, I think I should explain this. K, yeah, this k I write as lambda times p plus q times k. This is p plus q times k minus lambda np times here e power, no, p power k q power n minus k. That much I have. So this is equal to e power minus lambda n epsilon, and then here summation. So you take p, here I have lambda p k lambda n p k. Yes, so let me write here p power k e power, here I have lambda qk, and then q power n minus k, and then e power whatever remaining thing I write, and that will have lambda p is common n minus k, correct? Yeah, so this is equal to e power minus lambda n epsilon summation p power. So now p e power lambda q, okay, power k times q e power lambda uh, q e power lambda p whole power n minus k. You group it like this. So this is a crucial step. And now use this inequality. Now e power x for any x, if you expand it, what will you get? You will get 1 plus x plus x squared by 2 factorial, x cubed by 3 factorial, blah, blah, blah. And you keep this x, so let's assume that x is positive. Then this is less than or greater than, I don't know, maybe greater than. Do I want greater than, or depending on values, positive or negative? Yeah, less than or equal to. No, this is actually for all values of x. Let's see. Yeah, it doesn't matter. So I want to keep this one, and then I want to keep only even powers. So this is less than or equal to x plus, here I write e power x square by 2. Okay, this is correct. Yeah. So I use this in the next step. See, x is positive. I am not doing that. Let me see. Put it down here. Don't write that by 2, then it is okay. So this is something we have to. So it, yeah, it is some estimate. So I think that remaining things. So so I get 1 plus x squared by 2 factorial, and so on. Maybe the best thing to do is to prove this by using calculus. So use calculus to prove this. So it's very elementary calculus. I thought you can just manipulate the powers, but this is easy. Calculus to prove this. Okay. Then you use this in the following way. Let me say this. Here, I'm going to replace this and this using, so instead of e power lambda q k and so on, I'm going to use x plus. So I will have, each time I'm replacing by something bigger. So this is probability of Sn by n less bigger than or equal to p plus epsilon. Okay, is less than or equal to now summation whatever we have, e power minus lambda x is there, minus lambda n epsilon, and here this I rewrite like this. It's fairly complicated. So n choose k, but n choose k is very much there. Oh, I left out n choose k. This n choose k was present here and it's present here too. I cannot forget that n choose k factor. N choose k. And now this is n choose k times p. Yeah. So p plus e power lambda square q square power k times q plus lambda square, e power lambda square, a fairly complicated expression. Lambda square p square. I'm just applying this inequality, whole power n minus k. And here k goes from 0 to n. And now there is something that can fit into binomial quotient. So this is equal to, so a little bit more manipulation, less than or equal to e power minus lambda n epsilon times, so this n should be for the summation. I erase this and write here, otherwise it will be confusing. And you write here e power lambda square q square plus, see here there was, let me see, there was a negative lambda here coming. This was, I think it was okay. That we are taking care of that. Something's not quite right. There is a negative sign here. And that I should apply, when I apply that, as a minus p. So that's very important. You just don't blindly, you see, there was a negative sign. That negative sign, what was required here? Otherwise, there'll be problem. You see, where was that negative sign? Here, when you club these together, e power q lambda, here, this is minus q power. There's a negative sign here also. You see that n appears with negative sign. So I forgot this negative sign here. That is what gives this. So be careful. This minus lambda np, but here plus kp lambda. So plus kp lambda, there has to be a negative sign. Without the negative sign, it will be wrong. And now you use this binomial coefficient theorem. Here also it is p, I suppose. Yeah, that's p. It has nothing to do with p. So there is a plus p here and minus p here. This is how it appears. I'm just applying whatever I have. See, sorry, that's a slight problem. This must be there's a q appearing somewhere and a p appearing somewhere. P minus q. So let's write what we get. So this plus e power, so there is a q here, I'm sorry, this is q, but there it was a minus p. Okay, this is what lambda square p square, and then plus q minus p whole power n minus k. Right. Yeah, I think we'll assume that q is smaller than p. Okay, it's better to assume that. So at the beginning, let's assume that otherwise,
Sir, I think it's whole power, not whole power n minus k. The last line you wrote.
There's a minus p, right?
The last line. It's the very last line you.
There's a q coming from
It's,
here and a p
the whole
coming
power
from here.
n.
Huh? I get a q minus p.
So the exponent is not n. The exponent is not n minus k, sir.
Oh,
it's
sorry.
K.
Exponent is n.
I mean, it's just n. It's just n. Not
Yeah.
K. It's just n.
Just n. But this, I want to assume that, so assume that q is, so the book doesn't make that assumption, but I want to make this q is less than p. I don't know. Without that, this may be q is less than p. Then I can write this as e power minus lambda n epsilon e power lambda square q square plus e power lambda square p square whole power n. I need to think about what happens. If p equals q, then of course this is 0. But if this is negative, I can replace by this quantity. But if it is positive, then I am in trouble. At the moment, let's assume this and go on and see what we get. And now again, so I have, let me see, the complicated thing. So this, again you use one more inequality. I seem to be missing something here. Just 1 minute, I'll check. Sorry, I got a little confused. Need to check what is. This one. Rather than this, I have something else here. I write down instead of plus P and Q, I have something different. There's a Q times and not P. So here I had PQ, those factors. See, we substituted for e power lambda, e power lambda q, no? When we substituted for that, I forgot that factor. That is why things were becoming a little funny. So here is a P and here is a P and here is a Q and then plus Q times. Sorry about that, I made a bit of a mess. Here I still have P, here I still have Q, but here I have PQ minus QP and that term got cancelled. So I don't need to assume this. Sorry, I hope you follow. You see, there was a P times something. Okay, let's see. This P, I have this P and I have a Q here, and this was replaced by Q plus e power lambda square Q square. And here that was replaced by minus P plus e power lambda square q square. Maybe there is a lambda also, but let's not worry. So there was a lambda, perhaps there's also a lambda, q lambda, because x is lambda. So there's a lambda here also. Sorry, I erase and write properly. Yeah, it's a tricky proof, but these tricks one has to. So here I write power k and give myself more room. PQ lambda with a negative sign plus Q lambda. But Q lambda goes away, I suppose. Lambda, let it be there, it doesn't matter. Yeah, finally there's this times lambda and this goes away. And I have P lambda, Q lambda. Why is the lambda not there in the final thing? Sorry, I should have checked this before coming a little more carefully. I did that, but so the lambda has disappeared. When you come to here, why did it disappear? It's not clear to me. So, lambda seems to have disappeared from here.
So in the inequality e power x smaller than equal to x plus e power x square, like there is no like x term in the e power x square part. So like lambda won't be this. Like there won't be any lambda and like the e.
Here, there is
Yes,
no
sir.
lambda.
Yes, sir.
Why not? I am applying this for x is equal to p lambda.
Sir, I meant the p e power lambda square q square. Like in the I mean,
This pq lambda got cancelled nicely, but maybe there is no. So the book says there is no lambda. I don't understand why there is no lambda here. There
So
has to be a
what
lambda.
Rupert is trying to say is the p into e to the lambda square q squared, there won't be any lambda attached to that. Similarly, for the q into e to the lambda square t squared, there won't be any lambda multiplied multiplication factor.
Okay. But there is a lambda here. This lambda has to occur.
No, sir, the line after that,
The line
two
after
lines after
that. So we are applying this inequality.
You have
Maybe
no, sir.
it's a
The
stronger
line,
inequality. I
the
don't
line
know.
below that also, sir.
Here.
Yes, sir. The line which you're pointing right now. There is
There is
no
no
the
there is no
p
lambda here.
into yes, sir. Yes.
Oh,
The PQ lambda is right, but there's no lambda in the adjacent term.
why not? Am I not applying with x is equal to lambda p? Suppose I put x equal to lambda q, let us say, and there'll be a lambda q here. Okay, p times. Okay. P times p power x square. Okay, this p. Okay. We are replacing for this work quantity, and therefore there is no lambda there. Okay, fine. Yeah, okay. So we are going to apply this, correct, lambda p, but here p multiplies only here. So this is p and p. Okay, there is no lambda here. There is no lambda here. Let's, sorry, I myself didn't pay attention to some subtleties here. So this is q times. Okay. There is nevertheless a lambda here, but no lambda here. Okay. Okay. So that becomes like this. And then you rewrite this again in a slightly different way. I mean, each time, this is a very remarkable proof. So many inequalities come into picture. So this is less than or equal to minus lambda times n epsilon times e power lambda square n, that is it. Okay, so this is what we get. This p square, there's a q square here, but you just use some inequality and then derive this. So I'm saying that if p plus q equals 1, then some convexity property of this function, will tell you e power lambda square q square plus e power lambda square p square is less than or equal to e power lambda square n. So this is what we have. And now you rewrite this again. So there is a yeah. Let me just check once again if I have written it correctly. N square. Yeah. Now use an inequality that. So you basically what you do is you complete this. So this is equal to e power lambda square n. So this n can be taken out. Maybe that's better. And then use this inequality. Complete the square. So n times lambda square minus lambda times epsilon, and then you write here plus epsilon square by 4, and then minus epsilon square by 4. Okay, so this is equal to e power, sorry, that's an n again. And this quantity is, you can write it, so n times, what is this, lambda minus epsilon whole square.
So lambda minus epsilon by 2 the whole square.
Minus epsilon by 2 whole square. This is epsilon square n divided by 4. Okay. So this is some quantity. Now this was true for any lambda. Allow lambda to go to 0. Take lambda to be something small than epsilon. Why allow say take epsilon. Okay, no, actually I must take the limit. Take, this is true for every lambda. Okay, this is true for every lambda. For every lambda positive. So allow lambda to go to epsilon by 2 maybe, or allow lambda to go to minus infinity, I suppose. I don't know. No, whatever I do, it will not come out right. So what will make this small? I want to say this is less than or equal to, I'm sorry about this, I should have looked at this very carefully. Yeah, pick lambda to me. Okay, that's a good thing to do. Okay, epsilon equals 0. This is true for any epsilon positive. Take epsilon to be, take epsilon to be, lambda to be epsilon by 2. Then what do we get? Then this becomes, I hope there was no, okay. Then e power, so this becomes 0, probability of Sn by n bigger than or equal to p plus epsilon is less than or equal to want to say e power minus epsilon square. Okay. There's an n also here. I should have put here n square. There's an n epsilon, right? Totally confused. Hmm. Hmm. I'm really confused now. Hmm. Lambda square n by this one minus n epsilon. So I'm sorry, I made a mess. I will redo the last part again. We are close to the answer, but sorry, I should have been a little better prepared. So I'll stop here for today. I want to say that I had already posted, I hope you saw the message. I have posted the assignment number 1, and it is due on Sunday night, before midnight Sunday. Okay. Sorry about this mess. I will correct the thing tomorrow in the next lecture. All right. I'll stop here for today.
Sir, sir, I had a doubt. Should I ask it next class?
Yeah, you can ask me now. If it is a small one, I can immediately reply. Otherwise, I'll do that again tomorrow.
Okay, sir. So can you explain that Sn, the random variable Sn once again? How it counts the average number of
Sn, why it computes the average number of times?
yeah. How it counts the average number of occurrence of events A1 to AN?
Yeah, so you had this indicator function. When you take the value 1, if it belongs to, first of all, look at summation. Don't divide n by n. Just look at Sn itself. Sn counts in the number of times a particular. Okay, the Sn is going to be 1 if x belongs to union of these ans, correct? Okay.
Sn is going to be n if
Sn s okay.
if the event is in all the A1.
So what is, so you have to let us just think of it this way. This is the simplest way to think of it. You see, what is the meaning of the indicator function? It is going to return the value 1 if it belongs to AK, right? And is 0 otherwise. So what Sn does is, it looks at the first, if you want to evaluate it at omega, it asks if it occurs at A1. If it belongs to A1, if it belongs to A1, it says, okay, I'll keep track of it, 1. If it doesn't belong, it's 0. So Sn counts the number of AKs so that omega belongs to AK. All right. Now Sn by n therefore counts the average number of times omega belongs to AK. And this is exactly what I said.
Okay, sir, I got it. Thanks.
All right. Okay.
Thank you, sir.
Bye.